Yeah, this is because this event is broadcasted by YouTube, so we have to make it very tight time schedule. So 1:30. Yeah. Good afternoon, everyone. Thank you for attending the third International Symposium of the Hanyang Institute for Energy and Environment, HYIE. So we have prepared very grand theme, like driving climate technology innovations and carbon neutrality. So we're gonna have 3 guest speakers lecture, and then we'll have the round table today. I'm Professor Sung-Joon Kim in Department of Nuclear Engineering. As a Deputy Director of the HYIE, I'll be your host today. As the first part of the opening ceremony, President Ki-jung Lee of Hanyang University will deliver the welcome address. Please join me welcoming him with a round of applause.
Good afternoon, ladies and gentlemen, and esteemed guests. My name is Ki-jung Lee. I'm the president of Hanyang University. As the president of the university, I'd like to extend a warm welcome to you all. On behalf of the university, I also like to express my gratitude to everyone in attendance here today for this symposium hosted by Hanyang Institute for Energy and the Environment. I'd like to thank our distinguished guests and speakers for their participation, particularly those who have traveled from afar to be here for the discussions and presentations. Furthermore, to Dr. Do Hee-han, the SMR Platform Coordinator at the International Atomic Energy Agency, and President Paul Saunders of the Center for the National Interest, and Dr. Ram Pada, the Technical Executive in Energy Delivery and Customer Solution at the Electronic Power Research Institute. I also like to personally say thank you joining today's events. I have a few more people to thank, namely those from various domestic organizations, including Deputy Minister Kyung-won Song of the Youth Policy of the Directorate of the Prime Minister's Office, and Vice President Hong-gi Lee of Usok University. The theme of today's symposium is climate technology in the carbon neutral era, which of course is relevant to the common global goal of achieving carbon neutrality by 2050. Needless to say, energy technology innovation is at the forefront of this campaign as one of the keys to achieving carbon neutrality. For our part, Korea's national greenhouse gas reduction target is to reduce greenhouse gases by 40% by the year 2030, compared with the goal for 2018. Reducing the footprint in the energy and industrial sectors, which account for 71% of greenhouse gas emissions, is a top priority. Thus, to achieve this goal, coal-fired power generation must be replaced with renewable energy and nuclear power plants to fill the gap. Moreover, the demand for electricity has been increasing significantly in recent years, due in particular to the expansion of AI cutting-edge industries and construction of data centers. Subsequently, it is expected that the vast investment will necessarily be made to enhance the power generating infrastructure and to remedy some of the insufficiencies in power generation. Again, nuclear power plants and renewable energy are areas that are attracting much attention as sustainable power sources. These topics and others are the focus of today's symposium, which promises to be enlightening through productive discussions about what opportunities the AI-led electricity infrastructure boom will bring specifically to Korean companies. Progress for Korean companies will, of course, lead to future opportunities for cooperation in the power generating industries with other countries. In this regard, at Hanyang University, we are looking forward to working more closely and actively with the various related U.S. institutions and organizations. In closing, I'd like to again to welcome everyone here to third Hanyang University IEE Symposium. I wish you all the rewarding and inspiring day here at Hanyang University. Thank you.
Thank you. Thank you, President Lee, for your welcome message. Yeah. Before going forward with the congratulatory remark, we will first have a photo session with our speakers and VIPs. Two guest speakers, Mr. Saunders and Dr. Adapa, please come forward, and President Ki-jung Lee and Dr. Yeah. So we're gonna have 2 steps. So yeah. Okay, so please stay there. So please, yeah, I first, yeah, I like to invite the other VIPs together. Okay. Yep. Thank you. So that concludes the photo session. So thank you, VIPs, for your participation. So next is the congratulatory message from Mr. Kyungwon Song, Deputy Minister of the Youth Policy Directorate at the Prime Minister's Office. He will deliver the message. Please join me in welcoming him with a round of applause, please.
Good afternoon. This is Kyungwon Song. I work for Prime Minister's Office, as announced. My job is youth policy coordination among government departments. It is my great honor to deliver this congratulatory message at the third International Symposium of Hanyang Institute for Energy and the Environment. As I mentioned, I am involved in formulating and coordinating youth policies for the Korean government. And I believe today's topic is of great significance for the young generation as it pertains to the future agenda they should deal with and interested in. I sincerely congratulate everyone on holding this international symposium to discuss climate technology innovation, a topic that is both timely and essential. This discussion is even more meaningful as we prepare for the anticipated changes ahead of the inauguration of the Trump administration. The demand for electricity is expected to grow quickly in the coming decades. In a recent interview, Elon Musk recently highlighted this transformative vision, a future where electricity becomes the main energy source for almost everything. Currently, only about 1/3 of the total demand is met by electricity. As demand for artificial intelligence technologies continues to grow, electricity providers are starting to emerge as the next bull market. Nuclear energy has a critical role to play in supporting our clean energy growth and helping to deliver on the progress of AI. For example, 3 Miles Island, once known for America's worst nuclear accident, is now preparing to restart operation to provide energy to Microsoft. Google is another example of a company seeking cleaner energy. In 2023, 64% of the energy used by its data centers and offices was CO2-free, yet its carbon emissions increased by 13% within a year. Data centers' energy consumption played a major role in Google's rising emissions. Google is planning to use nuclear power to run its operations. Once again, I would like to extend the sincere congratulations to the organizers of this important event. I hope today's discussions will lead to productive discussions about some opportunities the AI-led electricity infrastructure boom will bring to Korean companies. Thank you. Thank you very much.
Thank you, Deputy Minister Song, for your congratulatory message. Now, Professor Yeon-gyu Kim, who is the director of the HYIE, will deliver the final part of the opening ceremony with opening message. Please welcome him with big hands.
The global common goal of achieving carbon neutrality by 2050 is accelerating. It is becoming a reality. it can be said that energy technology innovation is what determines the achievement of carbon neutrality. As our president said in his message, our NDC goal is to reduce greenhouse gas emissions by 40% by 2030 compared to 2018. Reducing the energy and industrial sectors, which is a big part of our emissions, which accounts for 70% of greenhouse gas emissions for us, is a top priority. And to achieve this, coal-fired power generation must be replaced with renewable energy and nuclear power plants at a rapid pace. As many said in their messages, artificial intelligence is a power-hungry hippopotamus. I don't know how many of you could understand this term. And as the demand for electricity increases with the expansion of AI, cutting-edge industries, and the construction of data centers, it is expected that a lot of investment will be made in the infrastructure. So nuclear power plants and renewable energy, the balance of these two in our energy mix, I think is the theme for today's conference, which is the third HYIEE conference. So I hope that today's meeting will lead to productive discussions about these important issues and opportunities coming with these. Once again, I'd like to extend sincere gratitude to our speakers and our participants from many departments on the campus and from outside. Thank you again. Hope that we have a great achievement today. Thank you very much.
Thank you. Thank you, Director Kim, for your opening message. Now we'll begin the lecture from our three distinguished guest speakers. The first speaker I will introduce is Dr. Doi Han. Like I announced in the beginning of the symposium, he couldn't make it because of his flight ticket was canceled. So he will deliver the lecture through the online. While we are preparing the online connection, let me introduce Dr. Doi Han. First of all, I'm very honored to introduce Dr. Han before the audience. Yeah, I saw him there. Dr. Han received a bachelor, master, and PhD degree from Department of Nuclear Engineering at Seoul National University. Dr. Han is a top-notch expert in small modular nuclear reactor, as he's serving in International Atomic Energy Agency as a SMR platform coordinator. Before joining the IAEA, he also served as the vice president of Korea Atomic Energy Research Institute in Korea. Also, he was a technical director for the Generation 4 Reactor International Forum. So with that, please join me welcoming Dr. Han with a big round of applause. Dr. Han, do you hear me? So your speaker is muted. Can you untagged? We can't hear you. Yeah, we tested many times, but it always happens at the very important moment. So we'll figure it out.
Yes, I can hear you now. So you can hear me well?
Can you increase the volume of your computer, Dr. Han?
Let me check.
Yeah, we barely hear your voice, very barely.
Okay, let me check.
Can you increase the volume of your mic, please? Is it possible to do it?
Can you hear me?
We barely hear that. Can you speak up your voice?
I can listen to you.
You need to be closer to your mic, maybe.
It worked quite well before.
Dr. Han, can you say something just to recognize your voice?
Yes, I hope you can hear me well.
Yeah, very low voice. Yeah, it seems to work, but sounds like the volume.
Best.
Okay, Dr. Han, I think we gotta solve this problem. So it may take at least 10 minutes. So why don't we start with Mr. Saunders? Then you give a lecture after him. Okay. Okay. So
That sounds a good idea.
yeah, please. Yeah.
Okay.
Oh, so please use that podium. Yeah.
All right.
Okay, seems getting wrong. So I think the Dr. Young-Gyu Kim is supposed to introduce yeah, Mr. Saunders. Yeah, please. Yeah.
Oh. Right. Always something happens. The morning of yesterday, I got a call from our staff that Han-do-hee missed the flight, 8 o'clock in the morning. Then again, we tested this. Then again, some technical problem again. So bear with us. Maybe we can solve this problem. In the meantime, let's get to Paul Saunders. Let me introduce who Paul Saunders is. Paul Saunders, I think he worked for the government, the U.S. government, as an advisor for State Department under some president, maybe.
The Bush administration.
Bush administration. So he was working for the U.S. government under President Bush, but then he's now running a research think tank in Washington, D.C. He's well connected to Korean companies as well. These days, he's kind of doing a lot of work between the ROK and the U.S. government regarding nuclear issues. Maybe he can share with us on some progress on, the nuclear development issue between the government, Czech government, and South Korea and U.S. company Westinghouse. Maybe he can share some news behind it. So please welcome Paul Saunders. He's speaking about U.S. ROK cooperation. Thank you.
Thank you very much, everyone. It's really a pleasure and a privilege to be here. And thank you to President Lee, to Director Kim, to Deputy Director Kim, and really to the entire staff here at the university and the institute. It's a great honor to be here. So we're talking about climate change and technologies to address climate change. And I will focus very much on nuclear energy and the prospects for U.S.-Korea cooperation working on nuclear energy. To take a step back maybe for a second, I would just observe that as President Lee mentioned, we're having a leadership transition in the United States. I expect we'll see a variety of different approaches, certainly to energy policy, climate policy as well. Nevertheless, I think even if President Trump does back away from, for example, the Paris Agreement, as he's promised to do, I do think that we may still see some very significant developments in the United States that could actually continue to drive down U.S. emissions, not as a deliberate matter of U.S. policy, but actually as a consequence of decisions taken largely for other reasons. And I'll talk a little bit about that. If we move to the next slide, so the global nuclear landscape is really evolving. It's changed very substantially over the last decade. I would point particularly to 4 factors: geopolitical competition, technological change, changes in markets, and changes in our policy priorities, and in that latter category, of course, the drive to reduce emissions, certainly being one of the very important policy priorities that's changed. If we go to the next slide. So I'll try to go through this very quickly, but if we talk about intensifying geopolitical competition and some of the impacts that has on energy, certainly we can look, first of all, in the security domain. We can look, secondly, in the political domain, thirdly, in the economic domain. I've listed here. Oh, thank you. Certainly. Thank you. I've listed here a variety of impacts in each of those 3 areas. I won't read all of them for you, but maybe just to highlight the first one, the war in Ukraine is having actually very significant impacts on global nuclear energy, really in multiple respects. Most narrowly, we see Russian forces having occupied territory in Ukraine, including the Zaporizhzhia nuclear power plant. And there have been a variety of discussions surrounding the security of the plant, risks to the plant. And these are all big questions that impact how nuclear energy is accepted globally. Secondly, we've seen a number of governments that had been relying on Russia for nuclear technology and nuclear fuel change their minds and go in different directions. And Professor Kim alluded to this when he talked about Central Europe, because Central Europe is certainly the principal place where that is occurring, and it's creating a lot of opportunities, certainly for American companies, for Korean companies, and others. And the final thing that I would draw attention to in this context, and this is really just meant to illustrate how many impacts there are, is most recently the Russian government has revoked the license from 10X, which is a subsidiary of Rosatom, to export nuclear fuel enriched uranium to the United States. And an American company, Centrus, uses that enriched uranium to make nuclear fuel. That's about 15 to 20% of the nuclear fuel that the United States needs. And this is part of the escalating economic kind of tit-for-tat struggle between the United States and its allies in Russia surrounding the war. So if we move to the next slide, here again I list a few points surrounding technological change. Small modular reactors, which we'll hear more about when we resolve the technical difficulties, but which really offer enormous advantages and many benefits in the nuclear sector, and this is driving the excitement and a lot of investment. Lower costs, greater flexibility, the possibility to use them for distributed power or in isolated locations, places where you may have a limited power grid. Some of the designs have particularly useful industrial applications. And in the United States, we're certainly thinking a lot about coal to nuclear, which is the idea that you would kind of take an existing coal plant and replace the coal boiler system actually with an SMR, and then you get to keep the rest of the site, the buildings, the connection to the grid, and much of the other equipment. We're also seeing a lot of other interesting things happen. New kinds of specialty designs being developed, like the floating nuclear reactor. Russia's Rosatom, which I mentioned a minute ago, already has one in operation in the Russian Far East, supplying power. Then we're seeing a variety of new kinds of designs, and many of you are engineers. I'm not an engineer. I won't try to explain the designs, but there are a number of new I shouldn't even say new designs, old designs that are getting new attention, including high temperature gas reactors, fast neutron reactors, molten salt, liquid metal, a variety of other designs. One other important aspect of this is new requirements for nuclear fuel and a new need for high assay, low enriched uranium, which is uranium enriched up to 20%, which many of these small modular reactor designs use. Today, Russia and Rosatom are the only commercial supplier of that. The United States is working to develop and has a pilot plant operating, but not yet providing that commercially. And finally, there's really a new emerging debate in the United States surrounding reprocessing of nuclear fuel, which had been suspended in the United States for quite a long time as a matter of policy, but that's something that's now being reconsidered. Could we go to the next slide, please? Then changes in markets. And I think every speaker actually has referred to this point already so far in talking specifically about artificial intelligence and the data centers that are required for that. Artificial intelligence data centers can require up to 10 times the electricity that a conventional server center would require. And U.S. electricity demand forecasts related to the adoption of artificial intelligence, show an average 9% increase in demand through 2028, which is really a shocking increase for a developed country like the United States. And when you think about our economic growth, being 2 to 3%, having electricity demand growth of 9% is really quite remarkable. Some other forecasts suggest that by 2050, the electricity demand surrounding artificial intelligence could be between 60 and 80% of the current industrial demand for electricity in the United States, just to give you a sense of perspective about what that means. Then I make here in the fourth bullet what I think in some ways is the most important point, and something that's really often lost in many of these discussions. The number of people globally who still don't have access to electricity or who don't have access to reliable electricity. And I think this is another powerful factor that we need to continue to and work to address. And then finally, I mentioned Russia a few times already, and I mentioned Russia because Russia actually currently dominates the global nuclear market. Russia holds about 70% of the contracts to build reactors globally. It has about 45% of global uranium enrichment capacity. China is building an enormous number of new reactors domestically, and once it turns its focus to global markets, I imagine it will be a very major challenger to Russia. But today it's focused internally. The next slide, please. And then finally, my point about shifting policy priorities, and those really affect globally the demand for nuclear and for energy generally. First of all, energy security. I talked at the very beginning about geopolitical competition. The geopolitical competition is forcing many governments to take a very hard look at energy security, and nuclear has been a big part of that conversation. We're here today to talk about climate and the desire to drive down emissions. Nuclear in that context really is an essential source of clean, firm, by firm I mean consistent and reliable electricity. And for many applications actually will be, I suspect, superior to renewables. Including certainly for the AI data centers, which is why we're seeing that interest. Finally, certainly in the United States, and I think in many other countries, one of the factors that argues in favor of nuclear is the question of land use. Nuclear energy and nuclear plants are able to produce very substantial amounts of electricity in a relatively small amount of land. And that's quite different from renewables, which have many advantages, and I don't mean to criticize renewables. They have many advantages, but one of the limitations of wind and solar is that they do have, relatively speaking, much lower energy density. They take up a lot of land, and in democratic societies like ours, that means there are more people who will live next to them, and more people who may not want to live next to them. And certainly in the United States, following the passage of the Inflation Reduction Act, which certainly has spurred very substantial investment in the renewable sector. It's also spurred growing rejection by local communities of the projects. The next slide, please. So now I want to just extremely quickly to apply this to the United States and Korea and our relationship with one another, and I'll try to do it across these same 4 areas that I was just talking about a minute ago. The next slide, please. So, the geopolitical competition can be a very major contributor, actually, to U.S.-Korea cooperation. We can work together to improve our energy security. We can work together to improve the security of nuclear sites, including cybersecurity and other concerns. We can work together to try to shape global non-proliferation norms. And politically, we want to compete with Russia and China for influence around the world. Certainly the United States is very much driven to do that. And the United States and Korea and other allies can work together in various international bodies, the IAEA and others, to coordinate our positions on these issues. Finally, we can try to work together economically, jointly financing projects, working together and putting together cooperative bids, integrating supply chains. At the same time, however, we have actually kind of one significant problem, which is that American and Korean companies compete with each other too. And we have to find a way to reconcile that as we pursue our efforts to cooperate. The next slide, please. Technologies. Technology is also providing many opportunities to cooperate. R&D, advanced manufacturing, certainly 2 of them. But the closer the technology gets to being a product that a company can sell, the harder it gets to work together because of the competitive issue that I just mentioned a minute ago. Reprocessing, highly controversial, certainly among some, but a technology that I expect actually to be coming back in the United States. And I expect that Korea would very much like to work with the United States on that. That won't be an easy thing, but it certainly may be possible. Finally, ensuring adequate supplies of HALEU, which I mentioned earlier, and actually after Russia's recent revocation of the license to 10X, not just HALEU, but nuclear fuel availability generally, certainly quite important. The next slide, please. Now, also, changes in the market can create a lot of opportunities. In the United States, the Congress passed very major legislation earlier this year called the ADVANCE Act, which for the first time allows foreign companies to own reactor licenses in the United States. That's a very major development, and I think a big opportunity for OECD members and for India, because this ability is limited to those countries to participate in the American market. There are certainly also big opportunities for the U.S. and Korea to work together in third country markets. That is somewhat constrained by the list of countries with which the United States currently has those civil nuclear agreements. There are probably about 40 of them. I don't recall off the top of my head. Finally, there are areas like kind of aligning our approaches to selling nuclear reactors overseas. which I think could be a valuable area for cooperation, although again not an easy one. The next slide, and this is the very last one, and I'm sorry to go on. So again, changing priorities. These also create important opportunities for the United States and Korea. In the United States, we really see increasingly bipartisan support for nuclear energy, driven in large part by a coalition of conservatives who are interested in, energy security, in exports, jobs, in national security, and liberals who are interested in doing something to reduce our emissions, and certainly also very interested in the jobs. Is that a coalition that could exist eventually in Korea? I leave that to the audience really to decide. But it certainly is a coalition that's been quite successful in the United States. The Congress has passed over the last 5 or 6 years several major new pieces of legislation to push forward nuclear. And my last point here, you can see, energy is really the ultimate political issue because it touches so many aspects of our daily lives. If you think about, moving around during the day and what you're doing, how much of it really touches energy, and if you didn't have that energy, how would your life be different? And because of that, energy is a highly political issue, and we see these kinds of questions. How much priority do you give to energy security? How much are you willing to pay for that? How much priority do you give to climate? How much are you willing to pay for that? Do you pay through higher taxes? Do you pay through higher energy bills? Because ultimately somebody pays. And in the era that we're living in now, particularly in the United States, but certainly also in China and in Korea and other places, how much of the technology and the systems are you going to make in your own country with your own workforce versus what you buy from others? So thank you so much for your patience and attention to me here, and I look forward to taking your questions when we finish. Thank you. Thank you.
Saunders. So so we're gonna have round table after all lectures are given. So the next speaker, I think we are a little ahead of time. So I just tended to get rushed. The second speaker, so we'll try again, the Dr. Do Han from IAEA. So let's try.
Can you hear me? Is it better? Can you hear me? Can you hear me?
Dr. Han?
I'm not sure.
Yes, little better, I believe. Can you maximize your volume?
Can you hear me?
we can, but there's a big howling though.
I'm not sure whether you can hear me.
Oh, okay. It's yeah, much better. Okay. Okay. Okay, now it's yours, please.
Can you hear me?
Yes, yes, Dr. Han. Yeah, please do. Yeah, please go ahead and give a lecture. Yeah.
Can you hear me?
Yeah. Do you hear me? No?
Now I can hear you.
You cannot.
I can. Yes. I
Okay,
can.
okay. Now I think yeah, it's doable.
Can you hear me now?
Yeah. Yes. Please give him a sign that we can hear. Yeah, we can hear you.
So, yeah, I can hear you well.
Okay,
So,
great.
Can I proceed?
Yeah.
Can I proceed?
Yeah, please.
Okay, thank you very much. First of all, my big apologies for not being able to participate in person due to the severe weather. And my responsibility at the IAEA is to coordinate all activities related to small modular reactors. And it's my real pleasure to have the opportunity to present global status in SMR technology development and deployment. Next slide, please. Next slide, please. Next slide, please.
Next slide.
Thank you. Now, first, I will talk about the role of nuclear in clean energy transition, and then I'll talk about small modular reactor status and trend, and then I'll briefly introduce IAEA activities, some of IAEA activities on SMRs. Next one, please. As you know, if we look at world energy consumption by energy source, the steel if you look at electricity, the share of electricity last year was almost 20%, and it was 10% in 1980. So
Yeah, so connection seems very unstable, and I think we just unlucky today. So We're gonna switch the speaker actually. The third speaker, please. I'm sorry for the this instance. We're gonna move to the third speaker, and the meanwhile we prepare the Dr.'s lecture.
Okay, let me introduce. We are talking about nuclear, this basic internet technology. But I still hope, I guess, that we could get some problem away. Maybe we could go back to Dr. Han-Do-hee. Hope. Now, moving on to our third speaker, Ram Adapa. I'm pleased to introduce Ram Adapa. He's from EPRI, Electric Power Research Institute. What is EPRI? EPRI was founded in Palo Alto, California, in the United States in 1972. For more than 50 years, EPRI has worked as a R&D network around the world, collaborating with more than 450 companies in 45 countries, and like a boast of 1,300 employees around the world. Okay, please welcome Ram Adapa.
Thank you very much. Good afternoon. Thank you for inviting me to this important conference. We heard from the earlier speakers about what is going on in the industry in terms of generation and also carbon neutrality, what we should do. The loads are increasing, the generation has to change with renewables, and also wind and solar, not only that, but nuclear power, we heard all that. But the missing point, the missing link is taking that power to the load. That's where my presentation is going to focus. So we need transmission and distribution to take the power from generation to the load center. So we have very existing, very old infrastructure, but we need to do something different than what we are doing so far in the future, because the loads are changing, the loads are increasing, the location of the loads are changing, the location of generation is changing. So some of the issues that I'm going to talk to motivate you, especially the young generation here, how to make this link from generation to the load centers in the most economic way, environmentally friendly way. So the next slide, please. First of all, I think some of these points, I don't want to take too much time. We have been covered by Paul earlier. President Biden's goal is net zero carbon emissions by 2050. Not only electric power, but all energy sources by 2050. That is the US goal. The next slide, please. The next slide. Yeah, and also in 2021, Biden has also signed 1.2 trillion infrastructure bill. That means we have in US, and I'm sure here in Korea as well, very old infrastructure. What I'm talking about is the lines, the poles and cables, all that, very old. They're working, but we are pushing to the extreme, so we don't know how long they work. So that's why they introduced this bill. Electric vehicles, improving power and water systems, also has $65 billion to rebuild the electric grid. That's there in that bill. The next slide, please. Now coming back to my beginning proposition of transmission. So we want to see what the existing grid is on the left side, where you have generation on one side, you have transmission, distribution, and the load on the other side. That's what our conventional power systems are. Power grid is. That's safe and reliable, but we have right now what is called on the right side the integrated grid. That's the way we have to operate now, because we have several technologies like wind and solar. They're coming close to the load center. It's not only producer but consumer as well, as we call prosumers. So something like that. We have to increase also resiliency, not only the reliability of the grid, but resiliency means when you have a hurricane or earthquake or something, the system has to have minimal impact and then it has to come back very quick. So these are our goals, the future goals for making the system more reliable and resilient. Next slide, please. First of all, one of the technologies I want to, a lot of you may know, but especially the young people, is power electronics. Power electronics is really taking not only the conventional power system of like transformers and breakers and all that with the wires, all that, but introducing power electronics to control the flow you want. When you have many variable generation sources like wind and solar, as you all know, wind doesn't have a constant speed, it changes. Solar, same thing. It's sunny today, maybe tomorrow it is not. So it changes. So we need to control the flow, right? So we can do that using power electronic controllers. These power electronics can change the way we operate the system for betterment, reduce energy usage, enhance the functionality of the conventional power system, enhance the integration of, enable the integration of the renewables, and also facilitate the creation of low carbon energy future. The red bullets there are very important. These are for US, 50% cut in carbon emissions by 2030. Net zero carbon power, the electric energy sector by 2035. Net zero carbon emissions by 2050 in all energy sectors, not only the power, but the gas and all other energy sectors. These are our goals in North America. And I'm sure the Koreans, you have your own goals, as we heard from the president of the university, Mr. Lee, earlier. So the next slide, please. For power electronics, you might be thinking, what is power electronics? Power electronics is there in every aspect of our life. As you see the power electronic spectrum here, 50 or 60 hertz, power line, DC is 0. Those are what we do in the power grid. But beyond that, you see the radio systems, television, microwaves, everything, all the way up to X-rays, MRIs, gamma rays, all these, they're all power electronics built. So power electronics is the key technology that we need to understand and implement in the right way to control the flows. The next slide, please. One thing that you need to understand, the existing grid, we have existing grid, works fine. Everybody will say, why change, right? But understand, when you put 100 units, say coal power, to a power plant, you get only 33 units out of it because the power plant has the inefficiency there. So the efficiency is only 33% for generation. Take that power 33, feed it to the transmission, then you get only 32.5, another 0.5 losses gone in transmission. Then the distribution has losses too. Then when you use, the worst scenario is the incandescent light bulb, very inefficient. Only 4 units will come at the end. You are putting 100 units, getting 4 units. That means there is a lot of loss in the system. So one way of thinking is, as Paul and everybody talked about, we are going to get increase in power. How do we get that? Yes, you can build new plants, new lines, all that. But another way of doing it is reduce these losses in the system. If you reduce the loss, you don't have to generate that extra energy that is going as a waste, right? So that is the key point I want to mention to you. So the surveys that we did with the electric utilities, the Kansas City Power and Light in US, we found out there's a lot of loss. With power electronics, you can reduce that loss in the all the way in the chain all the way from generation to the load. Yeah, I will show you some examples how we can do that. The next slide, please. For example, you take a home, a single family home, you can have energy efficiency improvements. Take out that incandescent light, put fluorescent or LED bulb. So you increase the efficiency there. You are not wasting as much energy as we were wasting with incandescent lamp. Heat pump replaces gas turbine. Then you have some efficiency. Then electric vehicles, plug-in hybrid electric vehicles replaces mid-side gasoline car. That increases efficiency. So this is one way of doing increase in efficiency in the residential and homes and other things. The next slide, please. Similarly, in the commercial and in residential and commercial sector, you can use heat pump water heaters, ductless residential heat pumps and air conditioners, improved ones, hyper efficient residential appliances. See on that in the residential side. Same thing on the commercial side. We are talking about data center loads 10 times. But if you have an efficient data center, maybe we can reduce the consumption by the data center. So efficient data centers, LED street lights and area lighting, variable refrigerant flow, air conditioning. These are all some of the improvements we can do in the beginning before we start building new power grid to meet the new load. The next one, please. Now coming back to power electronics in appliances. This is something we know. A lot of our appliances that we use nowadays have power electronics built in. So in the home, for example, the current configuration is mostly AC appliances, but in the future, we should have some AC appliances, but also DC as well. DC, especially with the data centers coming, with the computer loads and all that, even at homes, the DC plug-in is very useful because right now we are taking the AC, converting into DC, and then charging our cell phones and computers. Very inefficient way of doing it. If you have a DC plug-in, then you can directly put all your DC sources to that. Your AC plug-in for AC appliances. Down the road, at Big 4 conference, when I was there, they are actually demonstrated DC appliances can be made as well. So the whole house could be built with solar panel on the top, energy storage there, and then all DC appliances, everything like a microgrid concept. So they are connected to the grid. Only when they need, they operate. Otherwise, the individual home will operate by itself. Solar energy will charge the battery during night time. They use the battery to charge their appliances and lighting. The next slide, please. One thing at EPRI, our research, being a research organization, we do projections. What happens if we do all that? What I'm talking about. If you take in year 2000, the energy in billion kilowatt hours, about 3,500, you see that number. If you don't do anything, by 2030, that's almost going to be doubled, close to 7,000 kilowatt hours. This is the consumption of the total energy. But doing some things like codes and standards, market-driven efficiency, especially technical potential, that means doing technologies in the right way, reducing losses, as I mentioned. If you look at that, you can have increase in your load, but still you can maintain about the same level of energy generation that will meet your increased load because you are doing all these things. So that is the thing that I want to send the message across for the youngsters. How can you reduce your losses? What are the technologies you should focus on? So that your demand is increasing, but same time, you don't have to generate that much extra energy. Okay? The next slide, please. So this gives a little bit more details where the which of the sector, residential, commercial, industrial sector, heat pumps seems to us more inefficient, that we could get a lot more from them by having a high efficiency heat pumps. The next slide, please. Now coming back to, this is more North American centric here, the slides, but you could correlate them to Korea as well. We have, in the Midwest part of US, we have a lot of wind. Wherever you see the dark blue, wherever you see the red spots, those are solar. We have a lot of solar in Arizona, California, and some Texas area, and also some East Coast, you see that. So the load centers are at different places. The wind and solar at different places. We need transmission. So that's the point I would like to come across. Next slide, please. Now, we already talked about, balancing the load. You have the wind and solar, but we need some storage, because these wind and solar come at different times. We need energy all the time, right? So some of the, basically what I'm talking about here is the wind intermittency and solar intermittency. We need dance partners, we call. Within California, the state where I live, there are some targets, 20% by 2010 and 33% by 2020. We achieved already these targets for renewable energy penetration. Some other states in US, they have not come to that level. So in California, 1/3 of whatever energy that we use, that is either generated locally in California or it is coming from other parts of the country to California. So the next slide, please. Now, what are the technologies that we have is compressed air energy storage, which can have like 100 megawatt plant compressing the air under the ground when you have extra energy and releasing it when you need it. Then of course you have batteries and all that stuff, but those are very limited. So that's why we need to look at pumped hydro and other technologies where you can put more energy storage at the system level. Okay, the next one, please. Coming back to power electronics, you have power electronics at various levels. Building level, you see the PVs and all that, power electronics, plug-in hybrids, power electronics, smart end devices, ground-coupled heat pumps, all that. The next slide, please. Here, looking at power electronics in a campus like this, Hanyang University, you see a lot of places, even microgrids are there for university. Within US, we have microgrids where they have solar, wind, and all that energy storage within the campus itself. So even if you are connected to the power grid, like KEPCO here, maybe you don't need to take that much power. You have your own internal generation here to meet the load, and whenever you need it, only you take it from the grid. The next one, please. Now coming back to my area where I work is the transmission. What kind of controllers we can put to increase the flow on the lines, reduce the losses, increase the efficiency. So somebody just tell me what is the time when you want me to stop. I will stop because I have a lot of information, but I will try to get the message across very quickly. So looking back to power electronics in bulk power system, transmission lines, transmission substations, distribution lines, those are the places where you can put these controllers to limit how much power you can send it through them. And also you don't want to overheat the wires, because when you put too much power, they sag, they have flashovers, they have trippings, then you take the whole system down, which is not good. Okay, then it becomes a blackout or brownout, right? So you have to monitor them and control them with the power electronic devices. The next slide, please. One of the technologies that I work predominantly is high voltage DC, or even medium voltage DC or low voltage DC. The concept here is we are having generation mostly AC, alternating current. So converting that into DC using a power electronics converter called rectifier on one side, and then transmitting long distance, because DC is less, what I would say is high efficiency, less losses compared to AC. And that's why it is economical for long distance transmission, HVDC, or medium voltage DC or low LVDC. Then invert back again to AC using the inverter and then feed it back to the load, predominantly AC load. So that is the concept here. The next slide, please. So for this, we have been doing, the industry as a whole doing a lot of research. What kind of converters we need? So as you can see, two flavors of converters on the top. HVDC converters, current source, voltage source. Within that two types, again, there are several types of current source converters. There are two, again, line commutated converters, capacitor commutated converters. In the interest of time, I won't go through these too much details here, but you can always, get back to me or Google for more details of these. On the voltage source side, voltage source converters on the side there, also there are 2-level, 3-level, cascaded 2-level, modular multi-level converters, MMC we call. And then modular multi-level converters also have two flavors, half bridge, full bridge. Half bridge is the one predominantly being used, and then the LCC has been used for the last 50 years. You see the map here, years on the x-axis, capacity, gigawatts on the y-axis. The LCC is predominantly there for many years. Now the VSC is booming now, VSC half bridge, that is more economical. So this is what we see the trend, the VSC technology, voltage source converter technology. The next slide, please. So the difference between LCC and VSC is the operating device itself. Switches on and off, one per cycle. And then the VSC is IGBT, transistor based. It can switch on and off many times within a power frequency cycle. As you know, students, you know about this, doing the pulse width modulation and switching and all that. So, next slide, please. So the way they operate is these MMCs are the way to go in the future, for especially for offshore wind integration. They will have multiple modules, 100 to 200 modules in each arm of the converter. So a 6 pulse kind of bridge shown there. So when we do a MMC, you are actually eliminating harmonics, reactive power requirements. So a lot of advantages of VSC MMC operation. Only disadvantage is half bridge modules. When you have a DC line fault, the diodes we have right across those IGBTs will conduct fault current from the AC side to the DC line fault. Those are freewheeling diodes we call. To avoid that problem, we can have a full bridge submodules here that will take care of that. But then when you have full bridge, then you have more devices there, the cost is higher. So we can debate between this full bridge versus half bridge, or combination, some half bridge modules, some full bridge modules can solve the problem, or a DC circuit breaker is another option too, another technology. So these are some of the research topics that we are working on and the students can work on. Even in DC circuit breakers, what type of breakers you can do, use for this kind of operation. The next one, please. Again, here, this is a very comprehensive list of various functions and the comparison of LCC and VSC here. But a couple of points I want to raise is, when you're talking about DC power very high, like 10,000 megawatts, 12,000 megawatts, things like that, still LCC is the way to go, because that has been established and we know it operates very well for high power applications. For the low power, even up to 2,000 megawatts or 3,000 megawatts on the right side, voltage source converters are the good ones right now, because they have a better operating conditions, especially offshore wind, when we don't have any AC system there. It's all remote, and then we need to have a converter operating there without any AC system support there. So that's VSC is the best option. The next one, please. Footprint, the size of the converter station wise also. LCCs require large filters and then it takes more space. If you're looking at Seoul, for example, the city very congested, and you don't want to put a lot of space for a substation. You want to put everything together. New York City, Chicago, places like that too. We want to put compact stations. VSC is the better option. Offshore wind farms, straightforward application with VSC. Power losses, slightly higher in VSC, but the technology is improving and we would like to see those come down in the future, and the losses will be the same for LCC and VSC down the road. So the next slide, please. This kind of shows the HVDC lines and cables we have in North America. The red ones are the LCC and the green ones are the VSC technologies. One is the Transbay cable VSC in San Francisco Bay Area is shown there. And then cross sound cable in New York area, those are green. Wherever you see the green, those are new VSC technologies. Offshore wind, I think I have slides later. I will show you some of those applications as well. The next slide, please. Here, this slide, slightly different than previous one, shows what is coming up. Previous slide shows only the existing ones. But here, in construction, the green ones, you see in construction, and then the red ones are proposed in the future, the DC lines, DC cable projects. One of them is, you see on this side is Sunrise Wind near New York area, New York, New Jersey area. On the right side in the map, you can see Sunrise Wind. That is a new offshore wind application using VSC technology and cables, underwater cables. The next slide, please. This kind of gives you some statistical numbers in terms of current US DC scenarios. What is the megawatts that are consumed, commissioned in the US by the year? It's coming up very slow for the last few years, but suddenly it's going to go up again because of offshore wind and new projects that are proposed. For the last, say, 20 to 25 years, I've been working in this field. The technology was status quo, but last 5 years onwards or so, it's increasing a lot. Whereas China and India and other countries like Brazil, DC is going in a bigger way for the last 10-15 years. But in US, it was slow, but it's coming back now in a big way. The next slide, please. This is the Transbay cable project I was talking about, taking power from PG&E system, Pacific Gas and Electric, the local utility at one point, and injecting it close to San Francisco where they need reactive power. So having this VSC cable take real power and make that as a reactive power using these power electronic controllers so that you can operate the San Francisco load in an efficient manner than building a generator right in the downtown city close by. We had some, generators, old generators, they retired them because of space and pollution. So now, instead of building another generator there to support the load, we are taking generation from far away and then feeding it to the load center using this VSC technology. The next one, please. This kind of pictorial view of that station. That shows there where that red building used to be, where the generation is there. Now they built in front of that the converter station and all that. That shows the picture there. The next slide, please. This is another project in US using the railway corridor, putting a cable next to the railway corridor, taking power from the state of Iowa. Mason City is where the state of Iowa, and then Chicago area is where the load center, taking power from the wind power from the state of Iowa, feeding it to the load center using this DC cable, underground cable. This is the project. It should be completed by end of this year and should be operational next year. The next one, please. Another point I would like to make is, I talked so much about DC, right? How can we get this DC? You have to put converter stations or put cables and lines. We don't have, it takes a lot of time and money, but getting permits and all. So that question is coming from electric utilities in US. So what we at EPRI, we did is, can we do something with the existing AC grid, convert the AC system to DC? What does it take? So that's what you're going to see here. The next slide, please. For example, if you look at AC system on the left side, that curve shows your AC lines depending on the length in miles that is shown here, maybe you use kilometers here, but the lines shown there, 100 to 200 miles is voltage drop limited. In the first 50 miles or so thermally limited, then the stability limited. Anything beyond 200 miles, the lines, AC lines. That means even though AC lines has the copper and aluminum to carry the power, because they are integrated into the system, we cannot put too much power on them, otherwise they become unstable. So what we are saying is convert those AC lines to DC. By converting, we can get more power. There are several ways of increasing capacity. For example, you can use dynamic line ratings, the red bubble, and then the blue bubble is conductor retensioning, and then yellow bubble is reconductoring. Take the old conductors, put the high capacity conductors. And then the purple one is voltage upgrading. Substations, if you have 115 kV substation, make it 230 kV, double it. You can get more capacity. But the green one you need to focus. That is the one you can get a lot more power by converting an AC line to DC. The next slide, please. What does it take to convert? You keep the structures same. That means the poles and all same. Conductors, there's no change. Insulators, you have to re-insulate. AC insulators won't work for DC operation, because of the leakage distance requirements are different. So you need to put DC insulators, and AC substations, they don't work for DC. So you have to put converter stations, DC converter stations. Could be $200 to $300 million for every 1 gigawatt of converter station. It may cost you money, but you get more power on the same line by doing all this, sometimes re-permitting. So we did studies. We took the structures in North America, see which structures can be converted to DC. Look at the chart here, 115 kV, 230 kV, 345 kV, 500 kV lines. If you convert them, on the y-axis, anything above 1 per unit, you are getting extra power than what the AC power is. AC power is 1, anything above that. So there's a lot of potential, almost like a lot of conversions you can do and get more power on the existing AC lines instead of building new lines. That is the concept here. The next slide, please. One of the projects in Germany that is happening in conversion is they have a double circuit AC line, convert one circuit to DC, keep the other circuit as AC. They're able to increase the capacity by 40%. So next slide, please. One thing is with AC, we know we have the grid, right? Many nodes, and it also has to operate. But the DC lines I showed to you so far, they're point to point. But in the future, we will get a DC grid also with many converters connected in loops. So how do we control this DC also? Even though DC is controllable, if it is point to point, is controllable. But if everything is DC, then you need more controllers within the DC grid. That's the concept here we are working on to solve these issues when you have a DC grid. So there are several requirements. DC circuit breakers are required as well. So the next slide, please. So the 3 types of circuit breakers are possible with the DC: mechanical circuit breakers, solid state complete power electronics, or hybrid, some mechanical components and some power electronics. The next slide, please. Some of the prototypes have been done by the vendors shown here on the 3 types. Mechanical circuit breakers, they work, but if you look at the second response time, 10 milliseconds, that is kind of not enough for voltage source converters. You need to have, put them in 5 milliseconds or less. So certainly solid state circuit breakers and hybrid breakers are required for DC grid operation. But the solid state circuit breakers are very costly. So the hybrid is the way to go. That's the future. So that's what's happening in the industry. Next slide, please. The DC grids, so far, China has built them, 2 of them. You see there, the 5-terminal one on the left, and also the 4-terminal 500 kV DC grid on the right. In Europe, there are several projects that are planned. Even in US, we planned one Atlantic wind connection near New Jersey, New York area, but it's not going in the same way as we planned. It will change because the original plan and the wind developers are not going in that same direction, so things have changed. So the next slide, please. This is another thing in North America is we have predominantly AC grid with 765 kV AC. We are talking about a macro grid on top of that with DC, with many converter stations and connecting these AC and DC together, so we could have more power flow on those lines. The next one, please. These are some of the projects that are, I told you the proposed ones like the Greenbelt Express, some Midwest part of US to, so the western part, there is New Mexico, North Path, and the another project called Cimarron Link, and Clean Path Energy here in New York. There are several projects are coming up. So next one, please. Another one is SunGR transmission project. In it, this is also a DC. Next one, please. There is another concept called connecting all the continents together by DC cables. This was proposed by the Chinese few years ago. This is a futuristic one, but I want to show you the reason is different parts of the world have sun at different times. You can generate it and use these DC cables in the underwater cables and provide energy to different other parts of the world. So that's the concept that was proposed by Chinese a few years ago, but it's something for future to think about it. Next one. As far as the wind, I would like to have a couple of slides here. Wind generation in US is expanding in a big way. There are a lot of numbers here. I don't have time to go through it here, but one thing is UK is leading in the wind right now, and then the China is number 2, and United States is number 4 in terms of total capacity and all that. You can see their capacity under construction and all that. So we have in the Atlantic Ocean side, offshore wind platforms that are planned, and also the Pacific Ocean side near California. We are planning in Hawaii, we are planning Alaska, close to Alaska, we are planning. The next slide, please. So these are again some of the projects that we have been working on in US. You will get copies of the slides, so I won't have to go through that, but you can see those in the northeast part of United States, and the California and Alaska, the Hawaii on the top there, and some specifics of these projects, who are the developers and the names and the megawatts and all that. Next one, please. Just a blown up version of that. It's called North Atlantic and Great Lakes area. These are numbered. These are the wind development projects. The next one, please. This is the Mid-Atlantic. So total, you see about 50 projects. You can see the offshore wind projects in eastern part of United States. The next one. One thing is the eastern part is the depth of the water is not that much, so we can use fixed bottom wind turbines. But on the western side of United States, near California and Seattle area, we have very deep water, so we need floating wind farms with the floating cables. That's a challenge. So we are working on the technologies, how they can work for the floating wind farms. Next one. Cables, there are 3 types of cables that are used for DC. Those are given here: mass impregnated, self-contained fluid filled, extruded or cross-linked polyethylene. The third one is the most popular now. That is the one even for AC or DC, because it's like a plastic material cable, very lightweight. It can carry more capacity. The middle one is almost killed because the fluid can leak, environmental issues. Old projects, they were using it, but not anymore. The MI is still there for high voltage operation and all that. The next slide, please. Okay, this is how you integrate the offshore to the main grid, with different details are given in these slides. I want to have a time check and then I will continue, otherwise I'll wrap up here. Do I have another 5 minutes? Okay, so here AC wind farm configuration, you generate at 690 volts, the wind turbines, and then you step up to different voltages, and then different transformers are shown there, medium voltage transformer, converters, all that, and then you take it to with a AC feeder, take it to the main onshore, connect it to the main grid. This is the AC transmission. The next slide, please. This has some limitations. Around 30 miles or so, AC transmission, AC cable is not economical because it has a lot of capacitance. Cable means capacitance. So you need to provide reactive power to have the real power flow. So that's why the break-even, beyond the break-even distance, HVDC will be more economical. So next slide, please. So the HVDC, what we do is, you still have wind powers generate AC only, but you collect those to that yellow box there where you have that conversion AC to DC, and then you take the DC with a DC cable to the onshore and connect to the onshore AC grid that we have, existing AC grid we have. So this is the configuration. HVDC again has a lot of advantages you see here. So next one. There are several projects for offshore wind shown here. Most of them are in Europe and also some in China. On the left side, operating wind farms. Right side, planned wind farms with HVDC export cables coming in the next few years. Next one, please. Oh, so my conclusion slide here is many existing HVDC systems are 50 years, 30 to 50 years old. So life extension and all that going on. But the new systems are coming, of course, with the voltage source converters. Highest DC voltage for UHVDC is 800 kV in China and India. But they also, in China, they also built 1000 kV AC as well as 1000 kV and 1100 kV DC as well. Even 1200 kV DC, they have put some demonstration project there already in China. So because they need more capacity. VSC HVDC is increasing, as I mentioned earlier. So this is this part of the conclusion here. So next slide, please. So future trends in HVDC is really working with the new technologies, having DC grids, working AC and DC together, and segmenting the AC systems so that with the DC, so that when you have any outage, the DC will be like a buffer. It will avoid the faults going from one area to another area. So that way you can limit the blackouts to a small area, having DC either back-to-back or DC lines. So segmentation is important too. Next one, please. So the summary and conclusion is DC grids will be the future of HVDC transmission for offshore wind, also onshore. Major HVDC vendors developed prototypes of DC circuit breakers. Still more research need to be done by universities and students in that area of DC circuit breakers. You can come up with innovative ideas, more economical, less costly, still meet the requirements of 5 milliseconds operation. Hybrid breakers are economical. Multi-terminal systems built in China, I talked about already, and they are using hybrid breakers right now, but more work could be done in this area. So next slide. So these slides I will leave it because we have another speaker to work on, but just to give you one or two line highlight is, whatever I talked about so far, we use a material called silicon for power electronics. That is very reliable, but what happens is, when you want to increase the device rating beyond 10 kV or so, silicon is not good. So we are looking into new materials, silicon carbide, gallium nitride, combination of these we call wide band gap materials. These will be really good to increase the efficiency of the converters. So you can also start thinking of doing research in these areas with wide band gap materials for converters. So can you go to the next slide? So these are some of the benefits of these wide band gap materials. They have, still the material itself is defective, so we are improving the materials, but they have advantages. There are of course higher costs right now, But research, always we have to start somewhere, right? Even if they are higher cost right now, in the future, hopefully the cost will come down because they have very good characteristics. The benefits you can see on the left side, the high operating temperature, all that. Next one. So we do, at EPRI, we do projection into future, what happens, which devices can catch up. So you see that with the silicon carbide devices, and when they can reach higher voltages on the left, on the vertical axis, and the year by 2030, you can have like a 60 kV IGBT with silicon carbide that can save a lot of energy. So the next one, please. So EPRI is being a research organization, all the power electronic devices can save a lot of money, 1 trillion over next 20 years, if you have high efficiency power electronics, because all the power has to go through these power electronic devices. The next one, please. So this is my final last slide. In the wide band gap area, we still have to do a lot of work. But the Department of Energy, Power America Institute has put in $115 million to start working in this area. More work is going on by industry as well. Using these power electronic devices, the gallium nitride and all that, they are used in EVs, electric vehicles right now. But for power grid, we still have to do a lot more work because we're talking about more power, more capacity. So the next slide, the last one. So that's all I can tell at this time, because I know we have one more speaker. Hopefully he will come on and cover his topics. But certainly in the panel discussion, I can answer your questions. Thank you for your attention, and hopefully you learned something new. Thank you.
Thank you, Dr. Adapa, for great talk about transmission. Yeah. So we had the incidents, and we finally got a solution that I'm gonna present the Dr. Han's work. Yeah, I'm working on SMR, so
Okay.
maybe I don't wanna mess up his work, but if you allow me, then I will talk about the SMR technology development and deployment. Yeah. So, can I have laser point? So I believe Dr. Han is staying with us through the YouTube. So forgive me if I delivered the wrong message. Okay, so his presentation covers three major parts. Nuclear in clean energy transition, basically talk about there's some sort of a comparison between nuclear energy with some other energy source in terms of how clean or how powerful, things like that. And also the nuclear power reactor conventionally running based on the high power reactor. High power reactor means at least 600 megawatt electric. Up to 1400 megawatt electric, or 1.6 gigawatt to it's like gigawatt unit. But as compared to that, the recent trend in nuclear energy has basically the scale down, small modular reactor. That makes much manufacturing as well as the lead time in construction very friendly to the industry. That's why the SMR has come up with the market. So he basically intend to talk about what SMRs are. The last is some sort of IAEA activities regarding SMR. So I'm gonna deliver those three parts in order. Right. So here is the world energy consumption by energy source. The top line basically showing the number 1960. Right now we are 2023, 60 years. And look at the breakdown. Then here's the coal, oil, natural gas, bioenergy, electricity, and heat. If you look at the just yellow color, that is the electricity. So basically, in order to decarbonize our world, we are basically instead of relying on the fossil fuel, most of the energy's consumption has been electrified. So that basically shows that there's a much more activity on making electricity to reduce the carbon emission. And then in order to supply the electricity through the nuclear, then there is like a lower bound expectation and upper bound expectation. There's a lot of gap. Yeah, some says that, okay, at least like low case 500 gigawatts, and some reports said close to 1,000 gigawatts. That's a lot of change. For example, U.S. has envisioned that tripling the current nuclear capacity. Currently like a 200 gigawatt, and actually a year before last year they were saying that doubling, and right now they're saying that tripling. Tripling means that right now they have like a 200 1 gigawatt nuclear power plant, and making the tripling, which means 600 megawatt electric. 600 1 gigawatt electric. That's huge. That's huge. Why they came up with that idea? Because otherwise it's impossible to make the net zero or carbon neutrality. So we are basically playing between the low case and upper case and looking at the market. What are the possible market to for the nuclear? And so currently, although we all talking about SMR, still there are a lot of room for high power reactor. Let's say if we just set up the 100% of nuclear market, then still 40% are needed for high power reactor. That's based on the Korea Hydro and Nuclear Power Company, the Korean utility. And then still, okay, then the small modular reactor should be coming to play. Why? Because it has a better safety, improved safety, and it basically has a lower investment. So 1 gigawatt nuclear power plant requires at least several of $billion, which is a lot. Yeah, Westinghouse was bankrupted because of that. Now they are gaining some momentum though. But the small modular reactor, which makes like up to only 300 megawatt electric, you can just invest like $1 billion. So to the private funding, it's not a lot. It's accommodate, it's not really a big number. So that's why the small modular reactor has the market until like between 7 to 130 gigawatt, and I think at least 100 gigawatt. So then still we are talking about the CO2 emission, why we need to have the nuclear as well as the renewable. Look at this figure, then 2023, the left figure shows the global energy related CO2, carbon dioxide emissions. It's not slowing down, it is still growing very fastly, and it peaked out 2023 and it's going further. So unless we reduce that, then we'll see how it goes. So that's the kind of emergency situation. So maybe the possible practical way is to have the more nuclear and more renewable. If you look at the right-hand figure, then by putting into the nuclear, wind, solar together, then we can basically slow down the growth of CO2 emission. So let's talk about the nuclear and renewable then. Some people have some sort of bias idea, okay, renewable like wind and solar, they are very, very, very clean. But in terms of their whole cycle, you start to making the panel and the generation and transmit. During that period, you get the CO2 emission. So if you compare like a solar and wind and nuclear, then look at the nuclear. Nuclear is very comparable to wind. Yeah, still clean energy. Yeah, but somehow, public acceptance, that's sometimes like a digress from our scientific fact or objectives. But that's something we have to improve. And talking about land footprint, so there's a general rule that over the 100% of energy mix, if you have a renewable less than 5%, it doesn't affect any big problem in your total electric grid system. But once you have your renewable starting 10%, you get visibility issue because of this footprint. Yeah, look at the here. So in order to generate 1 gigawatt energy, electricity, the nuclear needs 3.3 square kilometers. The solar, wow, about 40 or 60 times, and wind even worse. So how can you accommodate those footprint? That's something that makes the visible issue. This is still okay. It just impair the just view. But if you have like more than 15%, then your total electric grid system has been going into the chaos. Yeah, especially that during the weekend with very bright sunny day, then solar and wind come into play and make a best generation. Then there's no industry activity. Then you have to shut down all the nuclear and fossil fuel and everything. The nuclear cannot restart in a day because of there's some characteristic. So that makes a lot of stability issue. Yeah. So we have to play with a very optimized combination of renewable and nuclear. So toward net zero emission, decarbonizing the power sector is essential to reach climate goals. If you look at the all power sources, we say that power to X. You generate power, then power will be used to certain X. X means electricity, portable, and industry and building and so on. That X covers all the consumption area. And look at this figure, then transportation, building. Transportation is not small, it's 20%. That's why all the people looking at the hydrogen vehicle and electric vehicle and so on. 20%, which is a lot. Even the ship, container carrier, there's a lot of regulation by 2050. Unless you came up with like hydrogen fueled or ammonia fueled or nuclear fueled ship, then you don't carry any container. That is a big problem, like to US, to Korea, and to other exporting country. That is a big problem. And power, still 40%. And industrial process need a high temperature, like a chemical or fiber. They need more than 500 Celsius degree of high temperature. Then how are you going to come up with that? No way with the fossil fuel, because it's going to be phased out. So because of this, nuclear have some very strong area that can play. So small modular reactor, let me talk about the small modular reactor a little bit, categorized into very small area. It was actually small and medium-sized reactor by the definition. But now, it has been changed into small modular reactor rather than medium-sized reactor. What modular means? Modular means many things. You can make a modular in stock, make many modular, small-sized modular, and whenever they need, they just transport and assemble it, so that you can reduce the construction period from 10 years to 2 years, which makes your financial situation more comfortable. You can reduce the financial cost from that. So the small inside by the IAEA, the 300 megawatt electric is defined as a small modular reactor, and reactor is of course the energy generated reactor, the chamber. So here, the large size is 700 plus megawatt. Small modular reactor is up to 300 megawatt. And rightmost figure, the micro reactor, up to 10 megawatt reactor. So keep in mind that if you have a smaller size of the nuclear reactor, then you get much better safety. Even the chance of accident even smaller than the Earth is heating by cosmetics, even smaller than that. Then, what is the disadvantage of having small power? Economy. You lose economy. Of course, if you have the higher power, then your economy is getting better. So we have to play with that, between that. So attractive features of SMR: lower capital cost, SMR, not the just high power reactor. The small size, modularization, and reduce the construction time and serial construction. It's like you basically put the first small modular reactor and then add a 1 by series. Then you can reduce the time and reduce the cost. And also the flexible siding and operation. So because the SMR has the better improved safety, then the siding can be more flexible. Also, if you have the improved safety of the SMR, then your SMR can be located very nearby the metropolitan, which means that nuclear power reactor can be used as the various types of the energy source, just not the electricity. So scalability, starting with a small reactor, then you can basically scale up the reactor. So like I said, diverse product like electricity, heat, and desalination, and hydrogen production. So those are the benefit of having nuclear. So SMR design, there's a lot of SMR. SMR is just a matter of size. But there's a lot of nuclear power reactor which use a different coolant. So conventional nuclear reactor use the light water or heavy water as a coolant. But in the 1950s, when the first nuclear reactor was developed, was tried to research it by concept, it started with a non-water reactor, like a sodium, liquid sodium, or gas. So the England still has the gas reactor. Nowadays, we are looking at those non-water reactor. Why? Because it can achieve the higher temperature. Having the much higher temperature, we get better usage, better application for high temperature process and the hydrogen production and desalination, things like that. So land-based water-cooled reactor and marine-based. Let's not talk about the nuclear propulsion submarine. So these days, the TerraPower, the Bill Gates firm, they are looking at the molten chloride fast reactor, which is a molten salt reactor, as the ship carrier, container carrier. They are working with the Core Power, which is the England firm. They announced in August this year. And in Korea as well, we are the Samsung Heavy Industry and Hyundai Engineering and Construction and Korea Atomic Energy Research Institute, supported by Korean government, is trying to build a ship carrier, like a 15,000 of container carrier. Yeah. So molten salt reactor is actually can be used for the marine-based. And micro reactor, liquid metal cooled fast reactor, which can be best usable for the AI center, data center. And the molten salt reactor can be used for hydrogen production as well as the high temperature process provider, supplier. High temperature gas cooled reactor, in US there's X Energy, working with the Korean Doosan Ability. They try to have the high temperature gas reactor up to 750 Celsius, then that can be used for the chemical company. So the Dow company, in US, I think that's the #1 chemical company in the world. They have the agreement with the X Energy to develop the high temperature reactor. So there's like a commercialized market. There's still need for market is growing on. And there's a variety of the SMRs are building very actively, very competitively through the nations. So here's a reactor technology for non-electric application. So look at the bar, the color bar starting from 10, 100 Celsius, which is very, very low temperature in terms of nuclear perspective, and up to 12,000 Celsius, used for like a coal gasification, things like that. So if you look at the 500 to 900, there's a high temperature steam electrolysis. So that is very essential for the hydrogen production. Yeah. So most of the non-water reactor, like a high-temperature gas reactor, small molten salt reactor, and liquid sodium fast reactor, they are targeting like more than 500 Celsius. So they can use for many different applications. So here is the SMR on the development, and if you go to the IAEA homepage, you can easily find what type of SMRs are on the development on the world. Officially, it's 556 officially, but as far as I know, there's like more than 80 SMRs under development, which may include one reactor in my center, molten salt reactor. Yeah. So here's the possible SMR on the development and possible deployment. So look at the let's look at here, detailed design like a new scale. We start with University of Oregon startup, and they finally got the IPO in Nasdaq. Yeah, so they have the construction with Romania to build the full new scale, and ISMR, which is the Korean Innovative SMR, which is under development right now. So we are targeting 2028 for the standard design certificate. And the BWRX IMSR, which is the molten salt reactor by the Canada Terrestrial Energy, they try to have the very, that is very, very interesting concept, but I'm not going to talk about too detail about it. And the BWRX by the General Electric kind of lose their some sort of like a leadership in the high power reactor. So they try to have the small modular reactor with a scale down from the BWR, so which called BWRX 300 megawatt electric, and they're gonna build that reactor in Sweden soon. I think that BWRX, in my opinion, will be the most fastest SMR in Europe area. And also SMR 300, which is the Westinghouse SMR, and the Natrium TerraPower, Bill Gates TerraPower SMR, and the Rolls-Royce, even the England. Well, that's not SMR, according to the IAEA definition. 470, but still SMR, small and modular, medium-sized reactor. Yeah, look at that. U.S. and England, Korea, and most of like nuclear country, like the country which has some leadership in nuclear. They are basically investing in the SMR, and even that, there's like a Russians one, lead bismuth reactor, lead cooled reactor, and China ACP, and so on. And high temperature gas reactor. There's many kinds of SMRs on the development. They are very competitive markets going on. So estimated deployment time here. So I think I explained enough in the previous slide. So challenges facing the successful deployment of novel SMR design. Basically, the biggest the priority is to make sure, to prove and demonstrate that the improved safety can be indeed realized. That's the first thing. And then by the serial construction and test and demonstration, you have to prove that your modular manufacturing is possible. Also from that, you have to come up with that idea that, okay, we can really reduce the total cost. That's the something. So secure deployment, implementing safeguard, demonstration of economic competitiveness, and the harmonization of regulatory part, that could be the bottleneck for the SMR development. So we need some sort of establishment of international legal and regulatory framework. So because there are a lot of growing interest in SMR among newcomer country, not only the developed country like the U.S., England, and like Korea, there are also a lot of countries who are interested in the SMR. take a look at here. So Algeria, Estonia, El Salvador, so on. Now, can you imagine that? So they're really into it. But I would say only a few countries can develop the SMR and put it into the market. So I would say only 5 or 10 SMR will be survived after like 20 years or so. This is just my personal opinion. It's not IAEA's opinion. Yeah. So key IAEA activities on SMR. Well, IAEA basically having some sort of control tower function, I would say. So technology development and deployment. So and the reactor technology assessment, you basically have to, I would say, enroll or register your concept or your design specification to the IAEA. And IAEA review and basically give you that, okay, your design is SMR or whatever the classification. That's what I knew. So, and then fuel safe management of spent fuel, radioactive waste, and decommissioning, so on. Approach to commissioning and operation. Of course, the most important part is actually right-hand side, safety and security. Also, the safeguard by design and the infrastructure development and technical cooperation. So every time of the year, and many times, all the experts in the world, they got together in the IAEA and discuss their design and talk about how to improve safety and so on. So IAEA is a center of the nuclear regulation development and safety. So that's what I understand. So integrated energy system, the future energy system will be much deeper with the current system. Yeah. So if you look at the left-hand side, there's a composite wind farm, composite solar panel, nuclear, and small modular reactor. They all got together. They are not going to be competitive. I mean, they have to be somehow very supportive with each other. Then those energy mix should be able to supply the necessary energy source to the grid and to the consumer. Then the transmission issue will come up with that. Yeah. And also the policy should be very important part between that. So IAEA regularly report like a safety report series. So if you're interested in SMR, then there's a really good report there. You can easily download those reports from the IAEA. So if you're interested in like a safety part, then there's also a lot of tech doc report. So it's very informative. And also SMR conference, those who are studying, you don't necessarily have to study nuclear. Yeah. If you have a little bit of interest in the nuclear, then it's very good to attend such conference. Yeah. The SMR conference. Yeah. So here's the top 10 country based on registration, like US and Korea 100. Korea is very interested in the IAEA activities, and France, China, Russia, and so on. Yeah, all the nuclear, all the company which has the nuclear technology, they got together and they share their view. So the nice thing about this SMR conference is that regardless of the national relationship, some has some hostile relationship, but as soon as the expert and or the scholars, they meet together, then they basically talk about the real one rather than very sensitive one. Yeah. So summary of the SMR conference. There's some issue about national sustainable energy planning strategies, including SMR, to achieve net zero emission target, and there's a lot of consensus that SMR will play a very important role on that. And transportable SMR, also supply chain for SMR is also very, very important. Yeah, like the US has some problem with the supply chain. Yeah, so, and the bilateral and multilateral cooperation between industry, government, and academia, they should work together. This is very unique area, nuclear area is. So, the nuclear harmonization and standardization initiative, the working group and technical group, they got together, talk about the regulator government side, and in the technical side, their technology holder, operator, so on, they got together and do whatever they need. So IASMR platform, which is the major job of the Dr. Do Han, serve as a focal point for the IAEA activity on SMRs and provide coordinated support and expertise from across the entire agency. And there's an SMR portal that provides latest news and all the information you may need. And then also the SMR school will be launched for increased awareness among member states interested in SMR. Yeah, so here's the email address. So if you're interested, yeah, please contact. So summary, on behalf of Dr. Han, I'm very, so unexpected today. But because I'm also working on the SMR, I could give a brief presentation today. And this is summary. It's obvious that the nuclear is expanding in terms of the nuclear carbon neutrality, achieving carbon neutrality, and also it's notable that there's various kinds of SMR designs, over 80 design. So we'll see, which one will finally come up to the first podium. And SMR can complement the intermittency of variable renewable. So let's get out from the bias. There's no perfect good or perfect bad, right? Renewable, nuclear, they should go together. Yeah, that is the bottom line, I believe. IAEA SMR platform basically assists member states. So if you're interested, then please visit IAEA homepage. Yeah, thank you. Okay, so we're gonna have 10-minute break, and then you can have the refreshment outside and get back here in 10 minutes.
So after the break, if you have questions, you can ask your questions to speakers. And 4:50, we are going to be ending our session today. Thank you.
들어서 저기 앉아 있어. 그러다가 쌤 저기 쌤, 유 선생님.
Okay, now speakers invited. Right. So those who are outside, ask to come in. So now we have all heard excellent speeches from all of our speakers. Now it's time to discuss some of the issues that are raised in presentations. We have exactly 60 minutes to go. So I'd like to have approximately half an hour for our questions and answers with our speakers. Then I'd like to open to the floor for about half an hour. So that's how we conduct this roundtable time. I have one big question, common question for our three speakers. Then I've also have smaller, maybe a couple of questions for each speaker. So maybe we can begin with a big common question, which is, I think given our discussions today, the main tone of our discussions is that, before we thought about reaching carbon neutrality, we thought about renewable energy as the only alternative to achieving this goal. But main message today is that we have another source of energy, which is renewable, nuclear energy. And they even said nuclear energy can provide many benefits, and nuclear energy can complement some of the problems of renewable energy. So my question to three speakers is that if renewable energy and nuclear energy can be in harmony in reaching carbon neutrality, why for a long time, why nuclear energy cannot be accepted as a clean energy? This is my question. How do we balance these two important sources of energy for carbon neutrality? What are the remaining problems for nuclear energy? This is my question. So maybe we could begin with Professor Sung-Joon Kim. Yes.
Yeah, I think that is toughest question for the nuclear community. So first of all, if we take this as very objective and very scientific way, then it's obvious that nuclear has the lowest risk in terms of the cancer or some sort of effect on public health. That's the science. But the problem is the conception, some sort of fear about the accident. So traditionally, we have three major accidents. In 1979, in US, there's a 3 Mile Island, Unit 2, severe accident. The core was melted by half, but that was very good system actually, pressurized oil reactor, and there was no radiological consequence on the residents, public. Even the President Jimmy Carter, actually visited just right after, one day after the accident, which proves that President there, which means that it's safe. So that is the fact. But but now the biggest problem was the biggest impression about the safety was delivered by the Chernobyl in 1986 in Soviet Union. But compared to modern nuclear power plant, that Chernobyl reactor is almost, I would say, they didn't have any containment. They kind of violate all the rules. There's no safety culture, and there's no good procedure. I mean, rules is not something that they have to follow. Rule was something they can easily break, which means that the safety culture was such bad. And then that action actually gave a very big fear to the European side. And then more recently, in Fukushima reactor 2011, that accident was actually caused by a tsunami, but tsunami itself didn't jeopardize the nuclear power plant. Rather, there's some mistake by the owner that regulator basically recommended that you have to make sure that your water barrier should be higher than used to be. It was like 5 meters. Actually, the regulation recommendation was higher than 10 meters because of the historical tsunami was expected 14 meters. So they didn't respond to the recommendation, the regulation recommendation. So when we look back, all the major accidents, the accident, let's not talk about Chernobyl. I mean, it is really joke, I would say. I mean, it's not acceptable design. So we talk about the TMI and Fukushima, then rather than their hardware problem, there was quite a bit of mistake by the operator action and by some sort of a protocol misunderstanding or some deliberately ignoring of the some sort of government order. So have to improve that safety culture. And so so I think that's why the fear has been some sort of accelerated on that problem.
Probably I can add one smaller question to that. Much better in terms of safety for SMR, but how about waste? Does SMR not produce any waste?
No. That's the totally misconception. I mean, SMR still does produce the nuclear waste, but we can categorize like a low level, medium level, and high level waste. But high level waste is almost the same as the conventional reactor, but the lower and medium level could be more because we kind of chopped up the high power reactor into the small one. But the managing low and medium level waste is not a really big deal. The biggest problem is the high level waste, which is the spent nuclear fuel.
Paul?
Well, just on the final point, I would observe, and you're the engineer, so correct me if I'm wrong, but some of the designs that people are looking at in the United States for SMRs actually can burn up the high-level waste, so you can actually reduce the overall amount of high-level waste that you have by using designs, and then it reduces the burden on the rest of the storage system. But let me make one sort of big point and maybe illustrate it with 4 different things, and I'll try to be fast. So life is all about choices, and there is not a single choice that you can make that's free. Every choice that you make has a cost. Okay? So nuclear reactors have safety risks. Everything has safety risks. But if you go back to your office or dorm room and search online for the research about deaths and health effects of coal-fired power plants versus nuclear reactors, you will find that the historical total deaths and health impacts of coal-fired power plants vastly exceed the historical loss of life and health effects of nuclear. Now, three other things here very quickly. We did some work in an organization that I previously worked for, looking at the state of New York. The state of New York in the United States, it's recently been a Democratic-dominated state. They've had among the nation's leading, most ambitious goals for reducing emissions and getting to a clean power system. And the state of New York also has actually huge advantages because if you look just at the state, they get about a quarter of their electricity from the very large hydroelectric dam, Niagara Falls. Some may be familiar with the falls. They get another huge share, actually, of electricity from some nuclear power plants in the state. So actually, before you even start trying to do anything to the power system, you already had like a 50-60% clean power system. However, New York kept failing to meet its goals because they couldn't build wind and solar fast enough, because people didn't want to have wind and solar projects near their homes. And the fundamental problem was that actually most of New York, so-called upstate New York, actually, because of nuclear and hydro, they had almost an entirely clean power system. The problem in the state of New York is New York City, which relies on coal-fired power and wants to get rid of it. But they can only get rid of their coal-fired power by going into rural areas in the state where people went to live to escape from development, and then building wind and solar. They couldn't do it, and they couldn't do it, and they couldn't do it. And eventually they decided, actually, that they needed to include nuclear inside their definition of clean power, because that was the only way that the state could meet its targets. Secondly, on renewables. I think renewables contribute valuably in a lot of ways. However, renewables aren't free. The air and the sunlight is free, sure, but you have to build solar panels, you have to build wind turbines, you need these high-strength permanent magnets, you need glass, you need steel, you need copper for extra transmission, you need all kinds of stuff. So the World Bank did a major study, I think, 4 years ago, where they took data from the International Energy Agency about what kind of expansion of renewables would be required, and other things, but mainly renewables would be required to meet the 1.5 degree Celsius targets they were trying to meet. And what they found was we need to have probably 4 to 5 times as much mining per year of 17 different metals and minerals. So is the world, are your local communities going to accept 4 to 5 times as many mines as currently exist? I think that's going to be hard. And that's a choice that people have to make as a society. And you can decide, that you want wind and solar, and that's the direction you want to go in. But if you make that choice, then you're also deciding that you want those mines. And you're deciding that, yes, we can get rid of oil drilling, and we can get rid of natural gas drilling, but we're going to have these huge mines instead. And that's kind of what the choice is there. Third point, wind and solar are certainly in the United States, especially with tax credits, are very inexpensive to develop based on what's called the levelized cost of electricity. The electricity that they produce, the cost of the project, and how that divides out. But that doesn't really take into account the total cost to the grid. When you build a lot of wind and renewables, and particularly as you build more and more and more of it, and the share increases, then the other things that you need to do in order to make that work become increasingly expensive. And the variability problem, you can certainly solve some of it with batteries, but batteries have limited duration. 4 hours, 8 hours, 12 hours. You're talking about kind of dealing with the variability. If the wind dies away for a couple of hours, or it becomes cloudy in the afternoon, or something like that. It doesn't deal with the variability between summer and the winter, or what happens if you have 10 or 15 days where it's overcast all the time, or where the wind is really low. And that turns out actually to be a much more expensive problem to manage. The other thing, the final thing, and I'll kind of end with this, the last thing you have to think about is, yes, you can have batteries, you can have natural gas power plants, coal plants, you can have nuclear plants as kind of balancing resources on your power system. But if every time that you do that, what you're actually doing is you're building two things to do one job. And what that means is that somebody is going to have to pay for that. And it's either going to be taxpayers or it's going to be ratepayers. People who are paying their electricity bills. It's either going to be taxpayers or it's going to be ratepayers. So let's say, for the sake of argument, that you build an SMR and you use that to balance your wind and solar. So you have wind and solar 25% of the time, and you're using the SMR 75%. Okay, but that SMR actually could operate 95% of the time. So you're kind of building something, and you're only getting 75% value, and actually you could get 95% value. So that's expensive. That's money that is lost by doing this. And as you build more and more wind and solar, and you have to do more and more of that, then this other asset that you build, balance, becomes actually even less and less valuable, and your losses on the other asset become higher and higher. So I'm sorry for that, and I don't mean to be critical of renewables. I'm trying to be open and kind of realistic, because we have to make choices as a society. Thank you.
Yes, just to conclude on that question, first of all, in US, nuclear power plants have been built for a long time. They have built, but then new power plants they have not done. The reason is public acceptance. Public, when they say in US, we have to take public opinion before you build any big plant like that. The neighborhoods will be surveyed, and then based on that decision, they will build new plants, whichever plant you build. So nuclear power plants in Tennessee Valley Authority area, and there are there quite a few of them, but any new plants, they were not getting approvals because public are opposing to the nuclear reactors. Several reasons. One is, of course, safety issue. The other one is, as we discussed, about the nuclear waste. Where do you dump all these things? There is Yucca Mountain. There are some areas they identified in US where they generate, they people are not that heavily populated there areas, and they put this stuff there. But how long? As the waste is coming on, and it's going to be at one point, people will be start living close by, and they will have effects on their lives based on these things. So that's my thinking is those are the ones that limited that application to increase to more nuclear in the past, but now it is changing with SMRs. They are saying that at least what I'm not working in that area, but what I hear from my pre-colleagues is nuclear waste will be is a less issue now. They can manage it, control it. They can take care of that, because one thing is the size itself is smaller now, 300 megawatt units, and the Google of the world, they are actually, instead of building gas turbines as standby generators, they're actually planning to build SMR. They're putting money in there. Google company has already announced they're going to have a microgrid with SMR as one of the source. This has come up as news. I mean, it's not done yet. That's their plan in the next few years. Same thing, all high-tech companies, they're planning to have these SMRs as their one of the sources. The second thing is renewable energy. Renewable energy, you can have 100% renewable completely, sure. If you want to have 100% renewable, as we discussed earlier, we studied actually at EPRI what it takes to have 100% renewable. Means no nuclear, no coal, except hydro. Hydro is considered to be a renewable power, plus wind and solar. If you do that scenario, we found that it's not going to be practical, because the reason is, first of all, system inertia. We don't have big plants. If we have something fails, the system will go down very fast. So 100% renewables scenario is not feasible. Plus storage, we don't have enough storage. We have pumped hydro facilities to store, only few locations they have identified. Compressed air energy storage, I mentioned that technology is there. They built with some funding in Alabama, one plant for 100 megawatts, they showed that, but still it's not there in a production way in every way. It's possible, but it has not caught up. Storage is still limited. Some people argue, well, all the EVs you have, you can bring them electric vehicles. No, you can use them as storage, as a standby, because when you come at home during evenings, they charge, and then you can use them as storage devices, because if EVs go in a big way, so they can be also used as storage. Some arguments are there. We did study what is the projected growth of EVs and how much they can really store, and can they give that back to the grid, or they just only use it for transportation. So we looked at all those options. Then we came to the conclusion that the future is going to be a mix of technologies. If you want to be 100% renewable, wind, solar, some percentage, it could be 50% or whatever, plus nuclear is the one, plus hydro. If you have hydro, of course, that's your first choice. And the nuclear with SMRs is the way that's being planned. That's even, as I mentioned, some of these high-tech companies are going with the SMRs on their own. Okay, so those are my comments. So what we see in the future is going to be a combination of all these.
Okay, excellent. Now, maybe you could go around with some individual questions. For Seongjung Kim, I heard that China is the only country that has commercialized SMR technology. Is this true? And second, in our former presentation by Paul in the material, it says that Russia and China are dominating global nuclear market. So at the moment, when SMR comes online, I mean, whenever, like a 2035 or 2030, how could America and the Republic of Korea can collaborate on penetrating probably the market dominated by China and Russia. And also second one, Russia is dominating fuel, nuclear fuel. So if you could, can you explain what this means?
Oh, yeah, it's very complicated question actually. There's no much open information from China. We know that China has built some molten salt reactor, like one kind of SMR, and some gas reactor in very small size. I believe that China. Yeah, I think almost pretty sure that China has already developed the SMR, but we need more time to confirm that whether their design is working as they designed. That's the important part. And the second, the nuclear fuel side, the Russia, people, we have the peaceful, period. The Russia basically, disarmed the nuclear weapon and made high assay, enriched uranium. We call it HALEU. HALEU has the uranium enrichment more than close to like 20%, lower than 20%. Actually, 20% is the limit for proliferation issue. So the HALEU is a very important fuel for the non-fueled reactor, non-water reactor, like high temperature gas reactor, sodium cooled reactor, and molten salt reactor. Yeah, so it's true that Russia could provide that HALEU relatively lower cost. Since the Russia's invasion on Ukraine, then all the channel has been blocked. So in the western side, like the U.S., France, and Korea, actually we are not the provider, we are the consumer. U.S., they are controlling the HALEU in their domestic area. So I mean, the White House, I believe that White House control that. France could provide that, but they need to, have the higher capacity, the production capability. So that's why they announced that they're gonna make the enrichment facility in Tennessee recently. So the way to resolve the fuel supply issue, then we have to be, politically, we need to have like political approach, like a nationwide approach. Yeah. So the KHNP in Korean side, their utility, and they're trying to have some contract with a HALEU provider like a Centrus or Uramco, or we may expand to the France like Orano, things like that. So that's the way that we can do. Yeah, and the other question, U.S. Korea. Yeah, so we have the very tight collaboration treaty between U.S. and Korea. So Korea cannot make our own rule in terms of the nuclear waste disposal, things like that. So in order to make the like a friendly environment, then we have to find the common issue between U.S. and Korea. It could be like a spent nuclear fuel process. So for example, the pilot process was supported by the Argonne National Lab and Korean National Laboratory, and then it's stopped by the Korean government because of some political issues. So the key problem is that this problem should be done on the scientific way, but somehow the political decision and policy comes in, then break up all the effort. So that's very sad part. Yeah, we have to improve that.
Maybe building on that, maybe we could move on to Paul. Could you explain what was going on, what is still going on between South Korea and the United States on nuclear issues in Central Europe, like Czech Republic and Bulgaria and others? Why the diplomatic role between the Republic of Korea and the United States. How do you see these moving forward evolve?
As I think we discussed a little bit earlier already, the United States played a very major role in bringing Korea 50 years ago. I'll repeat that. The United States played a very major role in bringing nuclear energy to Korea about 50 years ago. And today we have a dispute that's ongoing related to some of the intellectual property from that period. And it's a dispute between Westinghouse Electric Corporation on one hand, which actually is owned by two different Canadian companies, but is kind of largely operating in the United States. And I think as a result of that is sort of, for the purposes of this conversation, considered to be an American company. So Westinghouse on one hand and KEPCO and Korea Hydro Nuclear Power on the other hand are having a dispute about some intellectual property actually that was owned by a completely different American company that transferred the technology to Korea in the past, and then Westinghouse later bought that company. And bought its IP. And Westinghouse and KEPCO and KHNP had collaborated quite successfully, actually, in the United Arab Emirates to build reactors there. My understanding is that after that, the Korean companies wanted to sort of continue to develop new reactors in other places, and that was pursued in a way that, unlike in the UAE, didn't really include Westinghouse, and this led Westinghouse to raise this issue actually with the Trump administration, the earlier Trump administration, which kind of became quite concerned, and that led to the dispute that we have today, which relates to it's kind of playing out in lawsuits and arbitration and government negotiations. How that relates to Central Europe is that Westinghouse and the Korean firms are competing there to sell new reactors to various different governments in the region that in the past had actually Russian reactors and were relying on Russia for fuel. Now they've decided they don't want to do that anymore. And Westinghouse, while this dispute is underway, I think believes that it's in a position to block the Korean transactions from occurring, even though in the case of the Czech Republic, the Czech government actually has selected the Korean firms to do the project. So it's a very complicated and thorny dispute. It's a dispute fundamentally between companies, although on the Korean side, actually, the companies are government-owned. So that brings the Korean government into it very directly. And on the American side, even though Westinghouse is a private company, actually with Canadian owners, as I mentioned, there are kind of important policy considerations for the United States government relating to the intellectual property and kind of non-proliferation policy. So it's a very complicated problem. I understand that there's a proposal, on the table now that the Korean side is deliberating about. I certainly hope that everyone will be able to resolve that dispute, because I think it's an obstacle to a lot of the other things that we could do together. But it is clearly a complex and difficult one.
Right. So the clock is timing. I think that that public, I think we don't have much time. We have time until only March, but by that time Trump will be in. So somehow Trump, I think, I don't know, maybe South Korean government must pay for the designs and intellectual property rights, probably. So we'll see. Yeah.
It may be difficult to avoid that, but
Right.
I'm not going to make recommendations to the Korean government or the companies.
Okay, I understand. So to Ram, I guess that the final question, because time is running out. My question to you is that in your lecture today, in your presentation, we learned that grid infrastructure, whether to renewables or nuclear, I think it's very critical to the goals that we aim at, right? But in the United States, my understanding is that infrastructure is kind of suffering shortage. Is that the right way I understood?
That's correct, yes. Yeah, that's correct. But we are, that's why the infrastructure, what we are doing is the Federal Energy Regulatory Commission, FERC, which approves the interstate transmission lines from one state to another state. Okay, those lines have to be approved by FERC, the Federal Energy Regulatory Commission. Within the state public utility commissions are able to approve. Like in California, if you're doing some distribution expansion, the California Public Utility Commission can approve. Whereas if the energy is coming from, say, Nevada or Utah or some Midwest part of the United States all the way to California, then the FERC, the Federal Energy Regulatory Commission, has to. So, as I have shown to you today, there are many projects that are planned and being approved, and they are being built because of the shortage that what we have right now currently. The reason is initially the trend was, well, we will have renewables close to the load center. Do we really need this transmission? Because it may be, you may invest in this transmission, but you may not use it in the future. Then that's why there was some delay. That's why we found there are some issues of getting new transmission built. They got delayed a little bit because of that, conflict in the sense they don't want to put something as a stranded investment. Overbuilding transmission is not good, right? Because when you have microgrids, you have local generation serving local loads, things like that. So now we have gone through all that phase, and now we did a lot of studies. We found out we still need transmission. So the FERC already told us to increase the capacity on the existing lines. FERC Order 881 clearly states that first do a study, use dynamic ratings, measure the temperature of the conductor, ambient conditions of the environment, and try to increase or decrease the line loadings. That is another one. So all the utilities in US have to do a study, write a report, which lines they can really use the DLRs, the dynamic line ratings, how much more capacity they get. In some cases, they may get less capacity also. So those reports have to be submitted to FERC. So that's one aspect. The second one is the infrastructure bill released a lot of money that is given to individual utilities where they are expanding their existing grid, either by AC or converting some through DC. So they are building, upgrading the stations, building new lines, new things based on the infrastructure bill funding. Some of it they get from there, some local they have to pay by the ratepayers, things like that. So a lot of things are happening, but I think in the future we will have more transmission and distribution that is needed for sure. Okay.
Okay, excellent. Paul, seem to have
Yeah, if I
one
can
more.
just have a very brief minute. I wanted to answer your question to Dr. Kim, or give my own answer to it. This is the public acceptance question. So, I talked earlier about choices, and our democratic societies, everybody gets to make choices, and those choices are aggregated nationally and lead to national choices, right? So if we decide as societies that we don't want the mines, as I mentioned, that we don't want coal, we don't want natural gas because of emissions, we don't want nuclear, that we don't want to look at wind turbines, we don't want solar panels, and everybody gets to decide all of those things. Some people, will be in favor of everything that I just said. Some only parts of it. But if all of that happens, then the aggregate result of that is that we're making two other choices. Actually, one of those choices is that we're not going to have enough energy, and it's going to be really expensive. And the other choice is that we're going to totally miss the emission reductions targets. So I think that when people think about nuclear, or any of these other sources of energy, any of these things that we have to do, you got to think about all of it together, because if it doesn't happen, then we're making other choices, and there will be consequences for those choices.
Since you are saying it, let me add one more final question. What do you think of Trump's choice?
You mean the fact that he was elected?
Yeah. I mean his approach to
his energy policy.
Yeah, energy choices.
All right, sir. No, I can talk about that for a minute. So, first of all, I think President-elect Trump is really determined for the United States to produce more energy of every kind. And what he has said over and over again is that he wants America to have the lowest prices, energy prices, of any industrialized country in the world ever. Okay? So I think you're going to see an effort to produce more and more energy of every kind. He selected as his energy secretary designate a fossil fuel industry executive who runs an oil field services company that does fracking. And I think that points pretty clearly in the direction of greater fossil fuel production and exports. He certainly will be lifting the LNG export pause that Biden imposed. He'll be working with the Republicans in Congress to try to streamline and remove regulations and make permitting easier, and do a variety of other things. However, this energy secretary designate who I mentioned, Chris Wright, he's also on the board of directors currently of a nuclear energy company that's developing a microreactor called Oklo. And he has, Wright has signed kind of group letters of fossil fuel executives supporting nuclear. So I think we can expect the energy secretary designate, assuming that he's nominated and confirmed, to be a supporter of nuclear. He's also been, his company, I should say, has invested significantly in geothermal energy. And I mention that because I think geothermal energy doesn't get really as much attention as it deserves. And if you take the technologies that, mostly American companies have developed for oil and gas drilling, extremely deep drilling, horizontal drilling, fracking. If you take those technologies and you apply them to geothermal energy, first of all, you can do geothermal energy much less expensively. But secondly, actually, you can find sufficiently high temperatures underground in a much larger number of places. So it stops depending on kind of going to a certain place where there's sort of hot rocks that are not too far down, and you start to have a lot of different options. So when I was saying at the beginning that I think people might be a little bit surprised about the emissions impacts of some of the things that Trump does, actually, I think there's going to be more natural gas in the United States. Natural gas has been killing the coal industry in the United States. It's not renewables that have been killing the coal industry. It's gas that's been killing it. So as there's more natural gas, it drives that down. If there's more nuclear, there's a better environment actually for geothermal, and that becomes something that can be done. And if regulations are eased and prices are reduced, and that helps to deploy these technologies, actually, you know, I take nothing for granted, and anything can happen with Donald Trump as the president of the United States. But I think there are valid reasons to have some hope, actually, that American emissions could go down even as our energy production actually goes up.
Excellent, excellent. Because time is running out, we hope that we could finish everything by 4:50 as planned. So let me take questions from the floor. So if you have questions to a particular speaker or to all the speakers, raise your hand and tell us about yourself, identify yourself. Yeah.
Hello. My name is Bunjung Kim, and I'm not like I'm not in any engineering major, but I have a question to Dr. Adapa. I'm sorry if I mispronounced your name. You seem like a big fan of like high voltage direct current like infrastructure, and so I wanted to ask you, like, what do you think of like the sun cable project like in Australia? So because Australia has a lot of sun, they like have solar panels, and then they have like a very long distance undersea cable to transport the power to Asia. So what do you think of that project? Like,
Yes, the Australian project, they are also considering DC as an option for that because of the long distance. As I mentioned, cable projects, anything beyond 30 miles, DC is economical. Yeah, you're correct. So even though I'm working in HVDC area, let me tell the fact that if you look at all around the world, we only have about 250 to maybe maximum 300 HVDC schemes compared to AC, which is so many. So it takes a lot of time before you can see more DC, but it is coming. Okay? So the Australian project, to answer your question, is going to be DC, what I believe, because of the distance.
Okay, excellent. Next. Oh, Professor Park. Mike is coming.
I'm Young-Dok Park, of the professor of the Department of Global Climate Environmental Studies. Most of the discussion of conference is focusing on the nuclear. And then currently there are many talk about like the nuclear renaissance, even in the COP. So then, I want to ask him and Paul about this kind of talking about the nuclear renaissance can be sustainable, because the more talk about the nuclear, there is a more resistance from the many groups, especially for the problem of public acceptance. That's my question.
Yeah, let me go first. Yeah, your statement is in overall true. That there's going to be a lot of some sort of a structure between conflict structure between renewable and nuclear. But in other perspective, I would say in recent trend in Korea, for SMR, there's a lot of private company is investing, which means that I think that is a really good sign. Otherwise, because otherwise all the government, if the nuclear industry is just totally directed by the government, then always it's going to be like a flipped coin, depending on the government trend. So yeah, it could be, but if we have like some more dispatchable area to that the non-government company can get in, even the small company, then I would say the public acceptance could be enhanced, and so that some sort of a conflict between those parties can be, I would say, alleviated or in the long run. That's my hope. Yeah.
So I don't know whether it can be sustained or not. I think in order for it to be sustained, somebody has to build one, and it has to work. Okay, and after somebody successfully builds one and it works, and then hopefully more of them are built and installed and they work, then I think that's how it is sustained, and that's really the key. The problem is that decarbonizing the entire global economy is going to be extremely difficult. Okay, 78% something like that of global primary energy currently is fossil fuels. 78%. There's a very good kind of energy expert, I think Professor Emeritus probably by now in Canada, Vaclav Smil. He described the global infrastructure to extract, process, transport, distribute, use fossil fuels as the largest thing that human civilization has built. And I think that's probably correct. So if you think about trying to throw away the largest thing that human civilization has built, while it still has economic value, actually, in order to do something else, that becomes like very expensive and very challenging. And it's only going to be possible to have something else do all of the same things that fossil fuels do without producing carbon, and it can do it in an economically attractive way. It's the only way that any of this will happen. Industrial heat, system reliability, all of these things, we have to find a way to have it. And nuclear actually does that. And it exists as a technology that, setting aside the SMRs, which are under development, Generation 3 nuclear energy, that's a technology that we have mastered as a civilization. Hydrogen and electrolyzers, all of these other things, that doesn't exist. Actually, it's under development, it's expanding, but it doesn't exist at the same scale, and it doesn't actually. It's just going to be very difficult to make that work. If I the last thing I would say, kind of to quote Václav Smil again, the four material pillars of modern civilization: steel, cement, plastic, ammonia, okay, for fertilizer. If you can't decarbonize those four things, it's never gonna happen. Never gonna happen. So we need something.
Excellent points. I'm very sad to say that we don't have time. We have learned so many things, many questions asked, but still there are many questions unanswered. Maybe those unanswered questions may be for next time. Thank you very much for coming today. See you next time. Thank you. Thank you all.
Thank you. Thank you. Already said I didn't.
Thank you.